Okay. Hi, everybody. Thank you so much for joining us. We are going to go through some civil and environmental engineering mock lectures. And to begin, first off, we have Dr. Daniel Baker. He is going to do our first mock lecture here. So thank you for being here, Dr. Baker, and we're excited to watch.
Yeah, thank you, Shannon. Thank you, everyone, for being here, whether you're watching this live or watching this later. So I am a full-time instructor in civil environmental engineering, and I teach a good share of the statics and dynamics classes, which are classes that you will take when you come here to CSU, kind of after Calculus 1 and Physics 1. We start getting into applying these things in engineering context. So today I'm going to talk about a topic which comes from statics, probably something you're quasi-familiar with if you've taken any physics in high school, and it's going to be looking at slipping or tipping with respect to friction. Okay, so we'll do a couple of physical demonstrations. I end up doing in my classes about half lecturing and half what I call active learning, which is either doing demonstrations or having students actually work on problems, discuss things with their neighbors, whatever else. Okay, so a pretty interactive environment. So what we're going to look at today is if I have a shape, we'll just use this box right here. And we're going to put this shape here on a surface. Okay, so if this box is sitting on a surface, one of the things that I can do as an engineer is I can look at this and say, hey, there's some things going on here beyond just a box and a surface. I have some forces, right? So I have a weight of my box. I have what's called a normal force coming up here through this surface. And so what I can do is I can model that as what we call a free body diagram. And in a free body diagram, we're going to draw this body and we're going to add some forces to it. Okay, so let's go ahead, and here's our box. Cool. Now, one thing you want to do in a free body diagram is you want to isolate just the body you're going to look at. And so this is my box. This is the body. It has a weight. The weight's going to come down through a point we call the centroid. The centroid is this center. Well, centroid technically is the center of area. Center of gravity is the center of all weight in the body. But our weight's going to pass through that centroid. And then we had a normal force. And the idea of a normal force is that it's always perpendicular to a surface. Okay, so the surface in this case was horizontal, and so I can draw a little right angle line there showing this is 90 degrees between the surface to that normal force. All right, so we're not yet looking at slipping or tipping because I haven't basically pushed this box to do anything, right? It's just sitting here, and in this case, your weight's going to equal your normal force. And you can come up with that from an equation, the sum of forces in the y direction equal to 0. Okay, so I've actually gone through like 2 levels of abstraction here. We started with a physical box. We then created a graphical drawing, and then you could actually move into an equation. Now, I'm not going to write out all these equations today, just referencing essentially that this would be the next step, or what we call equations of equilibrium coming out of these free body diagrams. Okay, so one other thing I want to highlight here is that with this box and this surface, there's friction available between them. But in this situation here with the horizontal surface, I'm not using any of that friction, okay? So I'm just gonna write it on here just so we can kind of think about it. There's available friction, so I'm gonna put a little F here, labeling friction. I can say that this is available, but it's currently equal to 0, okay? So I'm not using any of that friction. Okay, so let's take a look now with this same box and the same surface, and I'm going to put a little angle to it, right? So my weight force doesn't change. My weight force is still acting through the center of this box, through the center of gravity down toward the middle of the earth. My normal force is going to rotate with my surface, okay, because it always stays perpendicular to my surface, and then the friction force kicks in to help this box from sliding along there, okay? So I can create another free body diagram. And so we have a little bit of an angle this time. So here still is my center of gravity. So my weight force, again, comes through the center of gravity. Now, notice over here, not only was the weight force equal to the normal force, but they were totally in line with each other. They share what's called their line of action. Okay, so the normal force is applied right in the middle here. It turns out that as we rotate this body, that this normal force actually moves. Now that might seem really weird until we think about what the normal force really is implying. The normal force is actually a modeled weight itself, which is looking at, it's an equivalent force to what's called the distributed load, right? So the force underneath of that surface, of that platform, is a distributed load, and we model that as one single normal force, okay? The distributed load, as we start to tilt this shape here, actually ends up being a bit of a trapezoid, okay? Where it's not a uniform value all the way across. It actually changes in magnitude underneath here. And so what we find out is that the normal force, if it's acting through the centroid, the middle of this, you can just kind of look at it and go, oh, the middle's about there. So my normal force is actually going to move over to about here, but it's going to remain perpendicular to this surface. Normal forces are always perpendicular. And then here, we're going to have our friction opposing motion. So our motion for this body, potentially it's going to want to slide in this direction. And so for our friction opposes motion, then we apply that going back in this direction here. Okay, so friction opposes motion, and we still can sum our forces and basically reach an equilibrium state with that body. Okay, so this would be the case where if a body was slipping, we may not have enough friction to keep it in place, right? Basically, if the friction is engaged, but that friction has limits. Okay, so I'm gonna do one more graph here as we're moving across. So if we think about vertically here, a friction force, and what I meant to draw horizontal, it's actually interesting. Most of my drawing these days is on a tablet versus on the board. So I think I've lost some of my whiteboard skills. And so you could think of this, the better way to think about it would be like a pushing force. The reason I want to use a pushing force versus the angle here is that we always end up using a sine or cosine of an angle, which is a nonlinear function. But to keep this as a linear function, our friction looks a curve something like this. And if you've been in physics, you've probably seen this before, where this case over here, friction equals 0, is this point right here, right? If we're not engaging that friction at all, we don't need any of that friction. This point here, we call impending motion. I'll just abbreviate that, IM. And then this part over here, we get into kinetic. All right, so if we're going to have this sliding, fundamentally, we've hit peak friction at impending motion, and then we've gone into kinetic as it starts to slip. So the last version, or the last scenario I'm going to take a look at is if I have such a steep incline. Actually, let me model this first. So I'm increasing the friction on my surface by adding some rug mat onto this. And so we're going to put my box back onto here. And probably not a big surprise that I can get a steeper and steeper and steeper and steeper angle. Oh, let's see what happens. What happens? It's going to start to, boy, it almost wants to tip and slip at the same time. So essentially there, we're reaching a point where we're having impending motion by slipping and impending motion by tipping. And so we can see there physically, I'm going to try to draw this much steeper here. So if I have my centroid still in the middle, and I realize I didn't draw a perfect square, but that happens, and my weight force is coming down here, what happens is this normal force, we said the normal force moved as this distribution changed. As we get to tipping, this normal force is going to come clear to the corner. Now it's going to remain perpendicular to that surface. Okay, there's my normal force. And here I'd need quite a large friction force. And we could imply that also because I added this rug mat to my surface, right? So that's going to increase my friction force. You need a whole bunch of friction to hold this in place. And what happens is that if this was actually going to tip, it turns out that the tipping would happen because the weight force gets past the corner. Once that weight force actually gets past the corner, this will physically tip over. So what we've created here are 3 different free body diagrams, which are based upon, like I said, this one here would be really my slipping free body diagram. This one over here would be my tipping free body diagram. And there's multiple different parameters that we can check in a given problem to see if we think it would either slip or tip. Okay, so I'm just looking at my time here, trying to keep it around my 15 minutes or so. So what we've covered is we've covered that we can take a physical situation. This is something we do as engineers all the time, is that someone comes to us and says, well, I've got a problem. I've got something I need to figure out. And we start asking them questions, figuring out how we can model that, right, in more kind of a graphical or a conceptual environment, then how we can set equations to it. Like I said, this is fairly light on equations. As you get into engineering classes, you're going to see more equations you'll ever want to see. So we'll keep that at a minimum level today. But like I said, we model that through a conceptual environment to create numeric equations so we can get some answers, right? So we can answer people's questions. And just in a nutshell, that's how we can use some of these principles and some of the, so you'll see a lesson almost like this. This is an abbreviated version of it. Hopefully when you come here and take statics with me in a few years. So I'm happy to take any questions that anyone might have. And you're welcome to chat those in, or you can just unmute yourself and give a shout.
Dr. Baker, what do you like about teaching statics and dynamics?
Oh, what do I like about it? I love statics and dynamics because they're really foundational. They're really like the building blocks of, and if you look at you can actually download kind of a flow chart from our website, looking at like what classes kind of come before each classes, and there's this whole kind of chain of prerequisites. And I love teaching statics and dynamics because I love getting students started on the right foot, that they can then take the knowledge from those classes and then just blast through. Not that obviously mastering statics means you're going to get A's in every other class after that, but getting started on the right foot is just a positive direction. It's also, I remember taking statics and dynamics, and it was super mind expanding for me to start seeing the world as forces and free body diagrams and equations and relationships. And it really changed the whole way that I see the world. And so if I can do that for students, that's what I love doing.
Thank you. You definitely did that for me. So one of my favorite professors.
Oh, thank you, Sammy.
Keep it up.
All right, I'll turn it over, and we'll leave some time at the end if you all have questions just in general about classes within our department or anything else. We're happy to answer those as well, even if it's not specific to our talks.
Thank you so much. That was awesome. Mary asked a question about which year this course would be, this course content would be taught. And generally it's after you take calculus and physics. And so it would be your first semester of your sophomore year is when most engineering students would take statics, and then dynamics would follow the following semester. So hopefully that answers your question, Mary. Thank you so much again, Dr. Baker, I appreciate it. So now we are gonna go to Dr. Omar Osbeck. She is going to do a little presentation here for us as well, another mock lecture. She's an environmental engineering faculty member, or professor, faculty member. So thank you so much, Pinar.
Thank you, Shannon, for the introduction. Hello, everyone. This is Pinar Omar Osbeck. I've been a faculty at CSU since 2008, and I've been teaching environmental engineering courses at the junior and senior level. I'm an environmental engineer from my undergrad, so I love the engineering topics. I love the environmental engineering topics, and I'm happy to share a little with you about one of the courses I teach. And I decided to pick a topic that is somewhat relevant to what we are going through nowadays in Fort Collins. So hopefully everything will work. Let me share my screen with you. May I get a thumbs up to ensure that everyone can see the PowerPoint? Thank you, Shannon. Perfect. And before I continue with what I have prepared for you, I need to tell you that my courses, especially when I teach face-to-face, I would like them to be really interactive. So I'll be asking you questions, and there are no wrong answers. If that's the answer that I'm not really looking for, I'll work with you. So please do not hesitate to chime in, including everyone, including Dan and Nicole here as well, because we only have a limited number of students at this point. So today what I want to cover is the water quality, water pollution, and the management techniques we can apply to ensure that we protect our surface waters. And when we cover this module, we have major points to go through. We start with the water pollutants and where they come from and what are their adverse impacts on the surface water. Then we take it to a little bit more focused on the rivers and mainly the dissolved oxygen concentration in the rivers, going through a process or analysis, what we call DO-SAG curve, dissolved oxygen SAG curve. And then we will take a brief look at the water quality in lakes and some management techniques that go along with it. Today, we have limited time, so we will be covering water pollutants and the sources and their adverse impacts. So we're going to be talking about that for today. So in the upcoming lectures, the upcoming topics will be covered. For today, I have two major learning objectives for us, and hopefully this 10-15 minutes will be enough for you to be able to achieve these learning objectives. By the end of this lesson, you will be able to list and explain the pollutants and their adverse impacts on surface water quality. And you will be able to define if a pollutant is coming from a point source or a non-point source. Let's start with an active learning activity. I hope the video will play well. I really want you to pay attention to what's going on in that surface water. You will watch kayakers going in, so I'll stop talking now and start the video for you. And I've tried it 10 times before it started, and it was playing, and it doesn't play the media right now. All right, I'm sorry for it not working. What you would watch with this recording is that the kayakers would go into the river, and as they go down the river, they would be splashed with black water. Anybody have any idea why that river is running black? Is it normal for a river to run black? I don't continue on till I get an answer.
I'm wondering if it's from like a fire up in the mountains, like the runoff from, I mean, I'm just guessing.
That is a perfect guess, Shannon, and that is unfortunately what happened in 2012. You can see the river ran black. You can observe in those pictures the sediments were black. And one of the reasons I picked this topic is we're going through wildfires again, and very severe and very massive scale wildfires in Colorado, unfortunately, again this year. But this was in 2012. I'll show you a little bit more. We had a lightning start a fire in the watershed of Potter River called the High Park Fire. It burned for about 3 weeks at a really, really high intensity. Similar to this year in 2012, we had really hot, really dry conditions for a very extended period. And the terrain was ready to burn anyways, and that lightning started all. And it burned over 87,000 acres. And at that time, it was the second largest fire in Colorado history, although we are breaking more records this year. And one person lost their life, and we lost about 260 homes. They were burned down and destroyed. So with those devastating effects, something else also came up with a major worry. What happens after a wildfire is that the terrain is different. The ground perviousness is different. You don't have vegetation to be able to hold on to the precipitation. So there was a major concern for extra runoff formation, and that flooding the areas, flooding the Potter River. A lot of precautions were taken. However, in about 2 or 3 weeks, or within that timeline, we had a significant storm event that did not flood, but carry all that ash from that watershed of the Potter River and carried it into the river, and the river ran black for days. And it was a major concern for, of course, the aquatic habitat, but also the local drinking water treatment plant as well. So with this, I would like to, before we go into the discussion of the sources of pollutants, I would like to maybe just ask the class, what do you think was in that water? Just a few things that come to your mind.
Ash.
Ash was definitely what was in that water that turned it black. What else could there be in that runoff, washing off through the watershed?
Can definitely pick up a lot of gunk along the way.
Definitely a lot of sediments, a lot of whatever's left behind in the watershed. Thank you, Sammy. Do I have one more? Any guesses what could be in that water? Think about what.
One of the students said burnt sticks.
Burnt sticks, thank you. Burnt sticks, burnt plants and trees, very good. And it could bring in other sources of pollutants. And I know we're just starting this topic, so let's go through what we have so we can figure out what are the specific terms we could describe those pollutants as. And thank you, Dan, for giving me the information from the chat. I cannot see the chat when I'm sharing screen. All right. The pollutants can come from two major different sources, and we describe them as point sources, and I have a picture up on the slide for you, and then they might also come from non-point sources. When I talk about a point source, as you can observe from that picture, it comes from a single point. You can identify where it's coming from, and you could go out there and collect a sample and see what is really in that point source. Typically, we have point sources coming from our domestic wastewater treatment plants or industrial wastewater treatment plants. They will have that treatment plant at some location, and with piping, they will carry the treated effluent, ideally in a cleaner form, and discharge it into an acceptable surface water body. The good part with this is because we know where it comes from and because we can identify and take samples and measure what's in there, we are able to track what's in there and go back and ask them to take extra measures if the pollutants are concerning. On the other hand, we might have non-point sources, and as that picture shows, it is runoff through the land, and wherever that land occupies, it could be from urban land, it could be from agricultural fields, and depending on where it comes from, there might be different kinds of pollutants coming in with that surface runoff. And it has so many points, so many drainage channels, it would be really hard to pinpoint where that runoff is coming from, and it would be harder to assess what is coming in, what are the pollutants coming in with that runoff. And if it's coming from an agricultural field, we might have fertilizers applied to that field or pesticides applied to that field, which would be concerning, but it would be still hard to control if the runoff is formed due to rainfall or snow melt. It would be also containing different kinds of pollutants and harder to maintain and control. The best we can do to minimize the pollutants for agricultural runoff is to utilize best management practices. Go out to the farmers and ask them to utilize just enough amounts of pesticides and fertilizers so that it would be absorbed by their crops and not left over to be carried with the runoff. For the urban cases, we do utilize salts for de-icing. We might try to minimize the utilization of salts or select salt varieties that might have a less impact, less harm on the environment. This table shows you the big picture of all the pollutant categories that we are concerned about in our surface water bodies and the sources that they come from. Is it a point source or is it a non-point source? And those sources are further classified as domestic or industrial for point sources and agricultural or urban for non-point sources. I would like to again start the conversation. I'm hoping to hear from you as we look into the kinds of pollutants that might be in our runoff or in our point sources. And one of the most concerning type of pollutants is called oxygen demanding material. So who has an idea what an oxygen demanding material do or be in that source? Typing to chat is perfect as long as Dan can help me access. Oxygen demanding, what does that mean?
Well, someone mentioned, I think it was earlier today actually, like algae.
All right, I want whoever that is, hold that thought for the second bullet point for nutrients. I do have that beautiful green lake. We were going to talk about algae in 1 minute, but that is hold that thought for a little bit for me. But thank you, Shannon, for letting me know.
And I was guessing that it takes oxygen, so it takes oxygen to live, and so therefore it takes it away from the fish.
Very good, Nicole. Yes, the term indicates that it should be consuming oxygen, and yes, oxygen demanding material does consume the dissolved oxygen in the water body, may it be a river, or it may be a lake. And I have that sad picture over there for you. The dissolved oxygen, like us, we breathe air, is essential for fish. And if we don't have enough levels of dissolved oxygen, we might lead to fish kill. The oxygen demanding material in surface waters mainly come from our waste discharge. It could be point sources, but it could be also from the decaying vegetation out in the nature. And then I have the answer to my second question: what would cause an algal bloom? And the answer would be algae. What would cause an algal bloom? It would be the nutrients, and nutrients mainly nitrogen and phosphorus, which are essential for us and essential for the plants and somewhat aquatic habitat as well. But if we have higher levels of nutrients, they will drive algal blooms. And algae has a lot of concerns. And I want to go back to the oxygen demanding material. While algae are living, they are photosynthesizing and actually producing oxygen. However, when they die and decompose, they will act like oxygen demanding material. Typically, the nutrients are present in detergents and fertilizers, so we need to control the point sources, or again, agricultural runoff. Pathogens. What are pathogens, or what is the concern with the pathogens? Can anybody give me a clue? In other terms, microorganisms, viruses, bacteria. Why do we care about them in surface water and eventually in drinking water?
They make us sick.
They would make us sick. Thank you. The pathogens would make us sick. Even if we have higher levels in a surface water body, if we use it for recreational purposes, we would be adversely impacted if we ingested bacteria, viruses, protozoa. And if it ends up in the drinking water, if we use these surface waters as source water, the drinking water could make us sick, causing waterborne diseases as well. And that cute picture is a picture of Giardia. Giardia and Cryptosporidium are the top two pathogens we are challenged with in the United States. Suspended solids, as you have seen, and that's the picture from that original example we had with the fire, come from particles, come from sediments. And good thing is, and with the fire, I said it just ran black for a few days because they typically settle out pretty readily. However, if they are smaller in size, they will cause turbidity. It's like smoky air nowadays for us, for our lungs. The turbidity and the suspended solids cause issues for fish as well and other aquatic habitats. So we would like to understand the levels of the suspended solids and make sure that we minimize the levels and ensure that they settle out if possible. Another concern is the salts. And salts, as I briefly mentioned before, might come from urban runoff from the streets. It might be also present in the industrial wastewater. As much as it gets treated, there will be still some levels. As you can see from that picture, it's a cropland, and if the water has higher levels of salts, it will adversely impact our crops. And if animal has access to water that has high salt levels, they will be adversely affected as well. Think about yourself. Would you like to drink ocean water? It would not be possible for us to live on ocean water. Same deal for animals and also plants as well. And another concern is with toxic materials. They might be organic or inorganic in nature, and they might come from agricultural runoff with the presence of pesticides, and it might come with the industrial wastewater discharge. One of the major concerns with toxic materials is that we cannot eliminate it. The aquatic habitat cannot eliminate it, which means that it gets it accumulates in our bodies and in the fatty tissues of the fish as well, and it leads to bioaccumulation, biomagnification. I have that smaller picture there. So the smaller aquatic habitat exposed to these toxic materials will again accumulate it in their bodies, and the bigger fish, which consume a lot higher levels of those smaller fish, will start the biomagnification process and will start storing more and more of these toxic metals, toxic materials within their bodies. And as we eat the bigger fish, we will be exposed to much higher levels of heavy metals and other toxics as well. So this is a concern, and it is important to make sure that we limit the discharge of heavy metals and toxics into our water bodies. The last two categories we have for the pollutants is the endocrine disrupting chemicals and heat. And I have a picture of a crab there, one claw red, one claw blue. Is that normal? What's wrong with that crab? Again, if you don't feel comfortable, please type it in the chat. Is that normal for a crab to have two different colors on the claws?
I'm going to say no.
Thank you, Nicole. It is a no, and it has a weird section in the middle as well. What I learned was if a crab has red claws, it is a female crab, and then if it has blue, it is a male. So the same crab having one female and one blue claw is not normal, and that is a crab caught in Chesapeake Bay. And you know that it is highly polluted there. Not every crab is like that, but the higher levels of contaminants, more specifically presence of endocrine disrupting chemicals, probably led that crab to have features of both male and female crabs. When we are exposed to these endocrine disrupting chemicals, because they act like or behave like the hormones in our bodies, will impact how our body functions. And for the aquatic habitat, they might alter their reproductivity, and fish populations and aquatic habitat populations would be impacted. One of the good examples for you I can give, because it got a lot of traction, was bisphenol A, BPA, in the plastic water bottles. It is an endocrine disrupting chemical that mimics, acts like a hormone, and drinking it, consuming BPA would lead to breast cancer, as you might already recall from what you have heard. So again, discharging similar compounds into the water bodies would impact the fish, but also would impact us as well. And lastly, I have heat as a category, and it is surprising. However, when you think about it, you realize that yes, heat can be worrisome too. Typically with the industrial waste discharge power plants for their cooling towers might increase the temperatures of the surface waters. The fish who prefer cold will be driven out. Also, higher temperatures lead to lower dissolved oxygen levels. Gases don't like to be constrained, and especially at warmer temperatures, it will be much harder to have them dissolved in water, especially the oxygen, so that the dissolved oxygen levels would be reduced. Again, if we have concerns with the oxygen demanding material, we would be creating a much worse case scenario. So with this, I want to go back to our original example that we started with, and I want you to take a look at these pollutant categories. And I know face-to-face is more fun, but I have a fun way for you to work with me as well. On your screen's upper right corner, it says annotate, and you can put marks next to those pollutant categories if you think that those pollutants were present in Poudre River after the fire and once that storm event passed and carried the ash and whatever else could be in the watershed into the Poudre River. So we're gonna take a minute. I will wait for you to put your marks in. Perfect. Thank you, Dan, for putting a check mark for oxygen demanding material. There could be more, so put check marks on the categories as much as you think as applicable. A lot of trees were burned, homes were burned, maybe unfortunately some animals were burned. All right, last 10 seconds. And I hope you had fun. Thank you for participating. And I got really good answers. We would discuss some of these further. For example, oxygen demanding material. There was definitely debris and ash carried through. It was an intense burn, but not everywhere. So even the plants were burned, they might still have the properties of oxygen demanding materials that could still further decay in the river. So definitely there could be some oxygen demanding material. Plants, again, bring in nutrients. One more thing I want to say about nutrients is that the firefighting also includes dropping of fire retardants, and some of them have phosphorus in them as well. So we could be putting fire retardants and nutrients in the form of fire retardants, and that they could contribute to nutrients as well. I got one check for pathogens with the burn, probably not so much than what we normally got, but there could be. Suspended solids, I'm glad we have one of the most checks there. Definitely much higher levels of suspended solids, maybe a little salts. Toxics could be coming from the homes that were burned from the wires, and maybe they had paints and solvents. Probably not as much endocrine disrupting chemicals, so we will discuss that further. And heat, when did that fire come? Was it fully put out, or did it still fall onto the burning area as it mildly was burning? It could also be bringing in heat as well. So with this discussion, I would like to end my lesson, and I'll be happy to answer any questions. I'll stop sharing.
I have a question. How long does it take? So let's say the fire, you put the fire out. How long does it take when you have these kind of fires that we're having till it kind of goes back normal?
I think it depends also on the efforts and the climate. The efforts meaning that putting back in native species and what else is going on. If we continue seeing dry periods as we observe this year, it probably will take longer. I'm not 100% sure, but probably it is more on a case-by-case basis, and it takes a different amount of time from one location to the other.
Okay, and then you have another question in your chat from somebody.
All right. How might they prevent contamination of the Poudre River? I think the best way would be to try to remove the fuels to minimize the wildfires and spread of it. But if it's not possible, it just with the runoff, it will end up in the Poudre River or in other surface water bodies. What we recognized in 2013 was that they already knew that the surface was changed, so the flooding was a major and real threat, and they put a lot of efforts for flood mitigation, and they were mostly successful, not 100%, but we can always spend so much money and efforts to mitigate it. So I think the focus right now, after we can put out these wildfires, the current wildfires, will be to minimize that flooding event, and that would reduce the contamination. But again, with these wildfires being quite severe, I think the most we end up with in the rivers is the suspended solids, which settle out relatively quickly. So rather than being highly concerned about the river quality, because it's gonna be much better within a few days or so, the worry is now on to the drinking water utilities that use the Poudre River water, or any surface water that might be impacted, to be able to treat it. And after 2012 fire, Fort Collins Drinking Water Treatment Plant put in a sedimentation basin to remove that ash before they could get the water into their treatment plants. So they already have a plan. For the other utilities, I've been seeing a lot of workshops going on, a lot of discussions going on, again, to minimize the impact on the drinking water utilities and us as consumers. So I would not be highly worried about the contamination in the surface water bodies, because I'm pretty sure they will they will make the efforts to mitigate the floods, to minimize the carrying of the ash. Great question. Can I answer any other questions? If not, I really want to thank you for participating, giving me the answers, checking the boxes for the pollutants. I really enjoyed covering this topic with you.
Thank you so much. It was awesome. I really liked it. It's cool because it's kind of my chance too. You know, I'm not an engineering student, so this is my opportunity to see what you guys actually do. So it's really cool. I love it. Our next lecture will be from Dr. Nicole Ellison, and she is new to our department and doing an amazing job. So welcome, Dr. Ellison, and I will let you take it from here. I guess. Are you there?
Going. Yeah, sorry.
There you are.
Great.
Okay. No. Okay.
Oh, I actually was just looking at something I want to play for you guys. So we'll go there next. So, and I can hear it in my background, so I need to stop it. And I'm not quite sure how. Can you guys hear it? It's kind of funny. All right. Again, so I'm Nicole Ellison. Let me share my screen. And I have a PowerPoint to share with you. So I am a new, like Shannon said, I am a new faculty member. This is my very first semester teaching here at CSU, and I'm so excited to be here. I thought I'd talk a little bit about my kind of journey here. I graduated with my first degree in '95 and was a practicing engineer for a lot of years, and then went back to school and got my master's started my master's in around 2010, and just recently graduated the second time with my PhD, which actually brought me here. And it was at that time that I had the opportunity to start teaching when I was working on my PhD, and I fell in love with it. So for all of those who aren't sure what you want to be when you grow up, don't worry. I think I just figured it out, and it took me about 25 years. So today's objectives. Can everyone see my screen, or can anyone see my screen? Can I get
Looks
a yes? Yeah?
Yes.
Okay, awesome. So today I thought we would do some introductions, me introducing myself, And then you've already learned something, so you're probably in good shape. But one of the things I like to do is I like to bring a practical application, which I think makes it fun. So I do have a video here that I'm going to play, and it's only about a minute. And this is a video that I shared with my class. And I made it to talk about why you're here. I definitely believe in the why. So if you have a why, I think you're going to be more apt to learn. All right. So I am going to bring you a tidbit from the materials class I'm teaching, Introduction to Civil Engineering Materials. And the really fun thing about this class is it really takes all of the materials that civil engineers use, and it looks at, you know, how are they going to behave, and how are they going to perform? If they're going to fail, how are they going to fail? And we can use those materials to design buildings and structures and roadways and wastewater systems, all of the materials that are used in design. And so with our class, we talk about several materials. One of them is concrete. We talk about steel and masonry and wood. And with every class, we have a lab that goes with it. And I wanted to show that to you as well. And I may have to reshare my screen. I'm going to stop it, and then I'm going to reshare it because I wanted to show you our computer lab. I'm sorry, not our computer lab, our materials lab, where we have the opportunity to things. All right, do you guys see my screen now? Are you seeing the lab or no?
Not yet.
Okay, all right, here we go. This, tell me when you see it. Do you see it yet?
Got it. Yep.
Got it? Yeah, so this is it, the CSU materials lab, and we're loading this beam, and you can also, I'm kind of talking over the graduate teaching assistant, and he's talking about the material properties. But the fun thing is we get to load it and we get to see it fail. And you can see the deflection right now. It's deflecting, and you can, if you look closely, you can see the cracks that are starting to open up horizontally along the beam. And it is still being loaded and it's still moving down. And actually at the bottom of the beam, you can see the fracture. Do you see the fracture at the bottom? So you can actually see the big crack. We actually were able to load it to failure. And I'm going to stop sharing and reshare my PowerPoint. But one of the great things we get to do with each of the materials, we get to go to the lab, and we have a 3-hour lab in which we can see how the materials are going to behave when they're loaded. And like I said, here, let me go on to my next slide. The other thing we do that I think is really fun, but of course I am an engineer, is we actually get to make our own concrete. And Loveland Ready Mix came in and showed us how to make our own concrete. Here's some postings from some students. We got to make our concrete. We poured cylinders that we put the concrete in and beams, so that ultimately, I think next week, we're actually going to break the concrete to see what kind of strength it has. The other thing that we talk about, can you guys still see my PowerPoint? Yes?
Yes, yes, we can.
Great. Then we also talk about wood. And I try and make it fun where I show you where wood is used. In the mountains, you'll see wood all over the place. This is a Double Slumbers Ranch. And so we talk about the material properties, and again, then we get to break it. Other thing that we talk about, and I know I don't have much time, so I'm going to go through things really quickly here. And then I actually have a fun activity for anybody who wants to participate. But essentially, we talk about, because of my background in engineering, and I have a background in forensic engineering, where I got to see things when they weren't working. This is a party that was in California, and they had a roof failure. And so we come in with these sample cases and say, okay, now you're the engineer. Let's talk about why it's failing. And we can predict the load capacity that it has. We talk about dead and live loading. We go into the building code. And we have scenarios where we can predict how much the structure can handle. And that prepares students for ultimately graduating and designing structures or becoming a forensic engineer. And we talk about other things that could cause failures, like defects in wood. Here on this side, you can see they've cut the joist where the duct is going through. So this is one of the exercises that we actually do in class. And we talk about, we build off of that statics that Dan was talking about, where we need to find the internal forces so that we can understand how the materials are going to behave. So in this particular exercise, we calculate the shear stress in the member. And then we also talk about things like allowable stress versus actual stress. So we always want the materials to be loaded less than they can take, because we want to have a factor of safety on our members. So this leads me to questions, but I also want to introduce the next activity. And for this activity, you'll go to goosechase.com, and here is a link to it. And I have shared with you a material scavenger hunt that my materials class did earlier this semester. And I think you have until 4 or 5 o'clock tonight, and you can take pictures. Basically, you download this Goose Chase to your phone, you take pictures, and you submit them. So here are some of the submissions. This particular team, I was looking for something flexible, and so they took a picture of a flagpole. And I was looking for something rigid, and they took a picture of, this is a building on campus. This was actually cracked me up, and so I shared this. One of my students, I asked for a bollard, and a bollard is something that withstands vehicular impact. And one of my students, I don't know, Dan or Pinar or Shannon, you're watching, they decided that a house could be a bollard. And I said, no, that house isn't gonna withstand a vehicular force. So I called my student out on that one. But other things we're looking for is materials that are subject to thermal expansion, and pipes and metals. And then another component that we talk about in the class is we talk about, is this building component renewable? Is it sustainable? So for everyone who wants to play, here's your game keys. I can have 5 team members and up to 10 teams per game. So I sorted it by school name, and you can take these down and you can play if you want to, kind of get to know your civil engineering materials. I'm going to leave this up, I think, for a minute and then take questions. I'm trying to go to my chat. Maybe I have to stop sharing to go to my chat. Do I have any questions?
Hey, Nicole, from your forensic experience, what's one thing that you wish every civil engineer would learn really well going out in the practicing world?
Oh, that's tough. I would say, having a fundamental understanding of loading, for one, because, so 2 things, a fundamental understanding of loading, because essentially you're going to be asked to predict the behavior of these materials. So somebody's going to come to you and say, hey, I want a bridge. And this bridge is in Florida, let's say, and they are going to ask you what it should be made out of. And so understanding fundamentally how the loading is going to occur and how those materials are going to behave is really, really important. And when you start to understand how the materials are going to behave, I always look at, when I'm designing something, well, how could it fail? Because number one, I don't want it to fail. So I'm always looking for those paths to understand how's it going to fail. Any other questions?
I so wish I understood more to be able to ask you questions. I just don't have the background to do it, but I think that was a great presentation.
Thank you. And, I was going to say one more thing about engineering. Do I have another minute or?
Oh yeah, please continue.
The great thing about an engineering degree is, you don't have to go in to be an engineer. My husband and I went to engineering school together, and he's a contractor and he never practiced. And the great thing about getting an engineering degree, I think, is it tells, future employers, hey, I know how to solve a problem. And the problems, as you all know, are changing every day, right? A year ago, I thought our biggest problem was plastics in the ocean, right? And then 6 months ago, I would say COVID is absolutely our biggest problem. Driving into work today, I'm like, the fires, that's our biggest problem. So that's one great thing, I think. Dan or Pinar, do you have anything to add to that?
I totally agree that we need engineers everywhere. With that kind of a training, with that mindset, we don't have to pursue engineering. We can also venture out for other fields as well. But personally, I believe that applying my skills and knowledge and passion to make this world a better place is really rewarding. And from environmental engineering students and also civil engineers, I know that they have that in their heart as well. To make the world a better place. And we do have our challenges and they change every day, which makes it a little bit more interesting. Even though it is sad, I look out the window, it looks like we're living on Mars nowadays, but we can always find a solution. And other disciplines, of course, too, but engineering has its means to be able to address a lot of these concerns.
So yeah, I think now we could open it up to kind of general questions. If students have any kind of questions about, you know, not necessarily what we just presented on, but just, you know, bigger picture questions about, you know, civil environmental engineering, or even life at CSU, or other things, we can help fill any questions you might have.
One thing I want to say about life at CSU, I love it here, and I'm so excited that I'm on campus 2 days a week, and my classes are optional to come. You do not have to come in person, but if you want to come, you can. Of course, you can't be sick. And I just being on this campus, it's huge, and everywhere I look, there are cool structures and you know, huge old trees, and it's a great. I'm really excited to be here and to be on campus. And I think we're what, like 60 or 70% in person with that option?
Yes, I would say that.
Yeah, I think it's like, yeah, about 65% have have a in-person component. So it's kind of a blend of a big spectrum. But yeah, hopefully things will clear out here in the next, you know, handful of months. And by the time any of you, I don't know if you're looking at coming in the spring or next fall, but I mean, another great thing about being an engineer is we find solutions. We find solutions, and certainly even just the, I think of it more as physical distancing than social distancing. I actually try to get my students to be as socially connected as possible. And I try to socially connect to them to, you know, maintain our relationships and everything else. So yeah, I think that being an engineer is being a problem solver. And it's one thing that, know that you'll be pushed to do. One thing I find that students coming in, often they're like, well, I was good at math, and so I thought I'd be an engineer. And we'll say that's awesome. That's a great first step. But what we're going to do with that math is we're going to teach you problem-solving tools that build on the math. Okay, so know that you know, being just good at math but not caring about solving problems may not carry you through engineering. But having a little bit of both is going to be an awesome combination for you.
And actually, there's a question here that says, what does the general course load look like for a freshman? Dan, is that something you could answer?
I think Shannon would be the most highly qualified person to answer that.
Well, Sammy, do you want to tackle it first, and then I'll?
Yeah, absolutely.
Okay.
I pulled up my 4-year plan just for reference, so I can give you an exact answer to that question.
Wow, it took me 5.
So your first year as an engineer at CSU is going to cover a lot of generic engineering classes that every engineer takes, regardless of whether you're a mechanical or a civil or environmental or chemical or whatever it is. You'll be taking math. The default math that people go into their first semester is Calc 1, but if you're way ahead of the game and you're taking Calc in high school, you can dive right into Calc 2 or Calc 3 or even differential equations. You'll also take a science course. So sometimes people start with physics, sometimes people start with chemistry. You can switch those up if you want, but both of those are required within your first year and a half-ish. You'll also take an intro to class. So if you went to the most recent Civil and Environmental Engineering info session for Engineering Exploration Week, you met Tom Siller, who was my professor for the Intro to Civil Engineering class. And that's just 2 semesters worth of an overview of this is what civil engineering is. These are some career fields you might go into. Here's a very brief overview introduction of the things that you'll be learning throughout your next 4 years here at CSU. And then last but not least, you get to take a series of core classes during your time at CSU. So these are not related to engineering. Everybody that goes to CSU has to take them. So you can take music appreciation, you can take like whatever. I'm in the honors program, so I get to take honors seminars about all sorts of random things. So that's typically your first year, is those general engineering classes, a little bit of an intro, and then later on, you'll start to converge into the more specific topics.
Well done. Well done, Sammy. You want to be an advisor for civil and environmental engineering? Yeah, I mean, that's exactly it. Usually it's about 15 credits a semester. And you do take those core classes as well. And then the beginning of your sophomore year is usually, like Dr. Baker said, when you'll start with statics, followed by dynamics, solids, that kind of thing. So yeah. I don't think that there are any other questions in the chat. Does anyone else have anything?
A question.
Oh, yeah, sure, go ahead.
So Dan and Pinar, how long did it take you to get through your undergrad? It took me 5 years.
I did 4 years, but I was lucky. I went to a state school, so I'm from Montana, so to Montana State, and tuition was cheap enough because I was an in-state student and I got enough scholarships that I didn't have to work. And so that was like a big player into like how long it took me. I worked in the summers, but I didn't have to work during the school year. And so that probably is the thing that enabled me to graduate in 4 years, because adding a working load on top of that, like I was, as a 15 to 17 credit student per semester, I was busy. And so you kind of have to find what your capacity is and kind of weigh it all out and try to figure out what the best route through it. But yeah, I was 4 years.
It worked, by the way.
It took me 5 years, but I took extra courses, and I'm originally from Turkey, and a state school in Turkey is practically free. So I did not have to worry about tuition when I was going through my education. It would not affect anything if I took extra courses as I went through.
Nice.
Years, yeah.
I will say too that we have quite a few students that end up on the 5-year track, especially if students are adding minors. There are a lot of minors that overlap quite a bit with either civil or environmental, but can still add 3 to 4 classes, which really would be about a semester. If you don't, with our curriculum, because we require 130 credits, if you don't do too many summer classes, you end up with a lot of semesters that are 18, not a lot, I guess probably 3 or 4 semesters that'll be about 18 credits. And normally that's like too much. So when I work with students, I try and kind of spread out some of those core classes to be taken in the summer. But I know like Dr. Baker now has worked out, I think we do statics and dynamics over the summer.
Yeah, and solids.
And solids, right.
Well, yeah, and actually all 3 of those classes and some more are being added in the online sections as well. And so if somebody is, taking a semester to go to community college or care for family or whatever else, like we're trying to add in more kind of flexibility in some of the early classes that you can actually get started before you even arrive here to CSU. Yeah, right. So yeah, I mean, I think a lot of students end up taking 4.5 to 5 years, or summer. Good. Oh, sorry, my dog. So any other questions? Class sizes, I would say, I think Dr. Carlson mentioned it earlier too. The earlier classes, Dr. Baker, how many do you usually have in statics? Like 150? 100 to 140, somewhere in there. So, the bigger classes, I mean, everybody's got a different style. Like I said, I try to do an active learning style where, basically you're in a big class, but you end up doing a whole bunch of work with the people around you. And so it's almost kind of like you're working in smaller groups more than you're really in a giant class. Yeah, I think early on, I'd say that 70 to 100 plus is not uncommon. And then as you get later and later, certainly you can have classes of 30 to 60, kind of depends on what semester you take things and whatever else, but they definitely get smaller through time. Because you also end up, like a lot of the early classes, I teach civil engineers, mechanical engineers, biomedical engineers, environmental engineers, and some like chemical engineers. I have all these different majors, and so I have a large number of students. But then as you get into your civil engineering specific classes or environmental specific, it's a smaller group of people.
Yeah, and I'll add to that too, because I get that question a lot on tours and stuff, is how big are your class sizes? And a lot of people are kind of scared off by the idea of big class sizes. And I think initially I was as well, but once you get into it, you really realize that it's kind of nice because it's like a choose your own adventure. Like, do you want to sit in the front and do you want to like maybe get called on, or do you just want to sit back and observe and go to the back of the class? Like, it's kind of really up to your comfort level and really makes classes like more approachable to what you want them to be. And in Dr. Baker's class, I sat in the back, not because I was a bad student, but just because all my friends were back there and we had like discussions and stuff during class, and I still felt like I was engaged. I didn't feel like Dr. Baker was a million miles away. And I also definitely didn't feel like super distant from my professors as far as being able to ask for help and things like that. So even if you're in a class of over 100 people, professors always have office hours, or they have teaching assistants that have office hours. So you are always more than welcome to go in and interact with them one-on-one if that's something that's really important to you. And if like you really value getting to know your professors, which is super important and a huge tip for everybody going into college, is it's definitely up to you to sit near the front or to go to their office hours or to shoot them an email or whatever it is. And the level of connectedness that you feel is kind of on you.
And I would say, I would add to that too, that even in this scenario that we're in right now with the global pandemic and things being really, online, that a lot of instructors are very available online as well. And I know I've heard specifically that Dr. Baker is very available for most of his students because I'm advising all of them right now in statics, and they're saying, I'm having trouble. And I say, have you reached out to Dr. Baker? And they say, yes, and he's been great. So yeah, and I would say that that's true of almost all of our faculty. Everyone is very available and very willing to help students and help everybody stay connected, even in this time that we're in. So yeah. Okay, well, gosh, you guys, this was awesome. The lectures were great. The questions were wonderful, and the interaction was great. So I appreciate everyone's time. And I think our next session for Engineering Exploration Day is at 2 o'clock with Dr. Carter. She's going to be talking about students' research opportunities within our department. So I want to thank all of our faculty and professors, Dr. Ellison, Dr. Baker, and Dr. Omar Osbeck. I appreciate all of you, and I hope you guys all have a great day.
Okay, thanks.
Thank you, Shannon.
Okay, bye guys.
Bye.